As I mentioned in the last part there, for the speed of light to be constant, everything else has to give. So distance and time have to be able to change. And that means that length needs to be able to change as well to accommodate Einstein's special theory of relativity. And this is that anything that's moving close to light speed appears shorter to a stationary observer in the direction that they're actually moving. So if you were if you had the Starship Enterprise from Star Trek, as far as the people who are on the spaceship are concerned, that's the length of it there. If you were at this point here and the Starship Enterprise was traveling towards you, or close to light speed, you would actually see it contracted. And yes, I know there's all the sort of practical difficulties of, well, it'll be gone past before you even see it, it's a thought experiment. So the equation that relates this is that you have the contracted length, L dash, there, and the proper length. So the proper length is as seen by the astronauts on the spacecraft, and that's then multiplied by this factor, the Lorentz factor. Again, it's similar to time dilation, square root 1 minus v squared over c squared. So contracted length is the L dashed. That's what you see from the stationary observer. Proper length over here is the what it's stationary. That's the speed that it's moving, and that's the speed of light in meters per second. So you're going to have a calculation to try in a moment. This was actually visualized, first of all, not with fancy computer graphics, but at roughly the time that Einstein was devising these principles of special relativity by a fellow physicist, George Gamow. And he came up with this book called Mr. Tompkins in Wonderland. And the observers here are the pedestrian and the policeman, and they see the cyclist coming towards them, again, shortened, but only in the dimension that they're actually traveling in. They don't actually shrink. They get compressed. So if the cyclist is going from left to right, the object becomes length contracted in that direction. So if we take this as, do we experience things actually contracting in length in our everyday life? Well, just like with time dilation, not really. The fastest thing that actually man has ever made is the Voyager space probe, which has now left the solar system, and it was traveling at 17,260 meters per second. And so what you can do is you can use that equation to show that the length is actually 3.9993378 meters. So it has shortened very, very slightly by nanometers even, in that direction that it's traveling by using the equation. Another thing you can use is a simulation of something called the Michelson-Morley experiment. So if you want to find out about this, then I would encourage you to read up about Michelson-Morley. But it was to do with, are we traveling through an ether where, or is empty space just empty space? So you can try that simulation there where you can put in the ether and you can have light rays that you can actually direct towards there, and it's a way of visualizing what's going on with that. But you'll need to read about the Michelson-Morley experiment. It's not part of higher physics, so it's just if you want to take it a little bit further. So what we've got is that speed of light is constant. We're using 3 times 10 to the power 8, but everything else has to change. So in terms of time, moving clocks run slow. That's the time dilation. And length contraction, things contract in the direction that they're traveling. And you've got both of those equations which are given. You just need to get used to using them.